Hello and welcome. Today, we're excited to present our research titled Out of Distribution Detection with Logical Reasoning. Our novel method integrates deep neural networks with a domain specific knowledge base, grounded in first order logic constraints. We demonstrate that this approach can significantly outperform current state of the art out of distribution detection methods while providing a certain degree of explainability. Out of distribution detection involves identifying inputs to a machine learning system that deviate significantly from the training distribution. These atypical inputs can lead to unpredictable system behaviors, potentially compromising safety in applications reliant on accurate predictions. Typically, OOD detectors map input data to a scalar outlier score. This score then serves as a basis for classifying inputs as either in distribution or out of distribution through the application of a predefined threshold. Current methods for out of distribution detection primarily rely on statistics of input representations in various layers of deep neural networks, such as posterior output probabilities, logits, or learned features. However, these methods tend to be domain agnostic, often overlooking the semantics of representations in relation to the specific task at hand. Moreover, they lack a straightforward approach to integrate prior domain knowledge, despite its availability in many applications. Finally, the decision-making process in these methods is generally opaque, offering only a scalar outlier score, which lacks explanatory depth. In this work, we propose a hybrid architecture for out-of-distribution detection. This architecture combines a machine learning-based perception system with a symbolic reasoning system. The reasoning system checks if the current input is consistent with domain knowledge by reasoning over a knowledge base represented as a set of first-order logic constraints. The perception system comprises multiple concept detectors, each predicting specific properties of the input. These properties could include aspects like class, color, or shape. We refer to the collection of predicted properties for a given input as its representation or state, and it is interpretable by design. In this study, all concept detectors are parameterized using deep neural networks. However, it's important to note that different parameterizations may be more advantageous in certain applications. The reasoning system consists of a knowledge base which contains constraints that restrict which observations are possible in the domain. This is achieved through an inference engine, which checks if the current state satisfies all formulas in the knowledge base. A straightforward approach for OOD detection is to classify inputs that violate any constraint in the knowledge base as OOD. Such decisions are explainable, as it is possible to identify which specific rules were violated. For example, if we encounter a blue stop sign, but our knowledge base implies that stop signs are red, this input would be classified as out of distribution. In our benchmarks, this basic approach outperforms random guessing. As the naive approach neglects the outlier scores of the individual concept detectors, the obtained results are suboptimal. To address this, we propose an enhanced method. Inputs violating any constraints in the knowledge base are immediately classified as out of distribution, while for others, we calculate the outlier scores as a weighted sum of the scores from each concept detector. We demonstrate that this refined approach can yield results that are either superior to or competitive with current state-of-the-art out-of-distribution detectors, including ensemble methods, while being able to provide explanations for the decisions in many cases. Our presented approach does have certain limitations. Firstly, theoretical considerations indicate that as the number of constraints and concepts in the system increases, there's a tendency to misclassify more in-distribution inputs as out-of-distribution. Secondly, this approach may necessitate additional labeling efforts. However, as demonstrated in our experiments, these additional labels can frequently be derived from existing prior knowledge. Thirdly, strict logical rules sometimes prove to be too inflexible to accurately describe the real world. For future work, we plan to overcome some of these limitations by enhancing the system with probabilistic reasoning capabilities. This addition aims to bring more flexibility and real-world applicability to our approach. Additionally, our source code is publicly accessible at the provided URL for further exploration and collaboration. Thank you for your attention.